In this, we are going to learn how to model one of the very important situation in the nature, what we call the impulse. So what's the impulse? So impulse means you can apply a you can apply a large force. You can apply a large force in a very short amount of time. So impulse means apply large force. So apply a a force, normally large force. Apply a force in a negligible amount of time. Negligible amount of time. Amount of time. So that's the situation. So you try to apply a force in a very small amount of time. So what are the situations? Like for example, these are examples. So let's say you can hammer a nail. So this is a situation. So you can hammer a nail. So let's draw it like that. So let's say so you hammer a nail. So like this, the hammer. So you're gonna hit on a nail. So that's the kind of situation. So this is one such situation. You can see that. So the question is, how long it's gonna hit on the how long it's gonna touch on the nail? So that's the kind of interesting question. And you can see that it's practically the time is zero. How long they touch each other. So that's one situation. So in this case, what we can do is we can model the nail, and then so you can write a differential equation for that, but the amount of external force, how long it's going to apply, is zero. So that's one situation. Let's look at another situation. So another one is so let's say you have a mass attached to a uh, string, so like that. So there's a string attached. uh, so in this case not no string attached, there's a string attached. So what's going to happen now? You're going to put an external force in that for a very limited amount of time, like you just like hit from like a pen or something. And then what's going to happen to the mass? How this going to behave? Um, what kind of motion this has. So this is the kind of situation there, and you can see that the FT you're going to apply for a very limited amount of time. So that's another situation. And also we can also talk about situation like this. So let's say you have electrical circuit, uh, so which has a resistor and also a maybe a capacitor and also a induction coil, but just a situation like that. So now what we can do is, so what we gonna do, we're gonna switch on actually yeah. So what I'm gonna do, I'm gonna replace this one with a switch. So let's look at this one. So let's say we're gonna switch on and off very quickly. So you can switch on and off very quickly. So that's a switch. So the question is, how the current gonna go in this system? What is gonna, how it's gonna behave? So like that. So those are kind of three situations where you can see the impulse response in a practical situation, and we can write for all three. We can write differential equations, and then we can solve them, and we can see how it's gonna behave. So that's an interesting situation. But the thing is that for to do that, we need a special kind of function, because you can see that that time is practically zero. So that means you should be able to represent that in a situation. So what we can do, we can define what we call a generalized function. We can define a generalized function. Um, Generalized function. So why we call it a generalized function? It does not behave as uh, the other functions that you normally know, because this function cannot be piecewise continuous. This function is not exponential order, especially not exponential order. uh, and also this has a kind of because we know that when you take the Laplace transform of function, that Laplace transform goes to zero when s goes to infinity, but that's not the case with this kind of function. So let's try to kind of understand what kind of function we need. So this is how we define. So what we're going to do, we're going to define a function in a special interval. This interval is going from what we call the from negative epsilon. When we say epsilon, that means a small number. So what happened in that interval? In that interval, the function is has a value. Okay? Only in that interval the function has a value, so that the total area under the curve is 1. So that's the kind of idea. So we can define a function so that this area is 1, whatever the epsilon we consider. So that means we know that in this case the width is 2 epsilon. That means to have a area exactly equal to 1, the height has to be 1 over 2 epsilon. Because when you try to find the area now, you can see that the area is simply equals to 1. Because you can use this rectangle, so the width height formula, you can see that the area is 1. So this function, what we normally call the delta epsilon t. Epsilon means it depends on the epsilon value. So you can see that whatever the epsilon except 0, whatever the epsilon, and you can see that the area stays the same. So so few things that we can see is, so you notice that one of the big thing that you notice is the area. The area of this function, the area below the curve, area is exactly 1. That's how we define the function, whatever the epsilon value. So now what's going to happen in this case? So let's see what will happen when you try to kind of make the small epsilon smaller and smaller. So what will happen now when you try to make the epsilon small? So that's the graph. So what we're trying to do, so let's start with it's a large epsilon. So let's say we're gonna go like negative 8 to 8. So so that means in this case the height is so that's the height, so we can draw it. So what should be the height? Because the area, the width is 16, so that means this height has to be 1 over 16 in this case. So now let's go half of this. So so if you go half of that, so now we have negative 4 to 4. So in this case 8, so that means now the height is 1 over 8. So you can see that in each time the area below the curve is exactly 1. So you can see every time this area is 1. So this area is 1. And then now if you look at this area, this is still 1, because in this case what we can do is we can take the height as 1 over 8. So like that, and then we're gonna go half of that. So so like this. So that's the kind of idea. So you can see every time the area stays the same. So it is always 1, always 1. No matter what the value is always 1. So this height is now it is 4, so it's 1/4. So like that. So that's the kind of idea. So even though we make the width smaller, the area below the curve stays the same, is always 1. So area is equals to 1 every time. So that means we can make much more smaller. So let's see another situation. So we're gonna very small value. So what will happen when get very small? This height goes to height getting larger and larger. So that means for very small value, so you get a very high value, but still the area stays the same. So area in this case is still the same, still 1. So yeah, so you can see when the value epsilon gets smaller, what will happen? The area, the height gets larger. So the height gets larger, but area stays the same. So area means what? Area means the integral. So if you, that means in other words, if you integrate from negative infinity to infinity, this function delta epsilon, that's the notation we put, t, if you integrate this function dt, it is simply 1. So this is one of the property of this special function. This integral always 1 equals to 1 because the integral represents the area. Now, and the other thing. So what's the other thing? We're going to define what we call the generalized function, what we call the Dirac Delta function as the limit of this function when epsilon goes to 0. So it's a kind of definition. So what we're going to do, we're going to say that we can define this one as, so we're going to say delta t, the delta function as the limit, when epsilon goes to 0 of the delta epsilon t, that function. But it's a kind of definition because this is not exactly what we do. We're going to define this function using properties. So we already have one property. One property is when you integrate, you get 1. That's the one property. The other property is, because of this limit definition, the other property is this function is only non-zero. We define like that. So it is 0. We're gonna carry it like that. We're gonna say this function is 0. So delta t function is 0 if t not t equal to 0. It's kind of interesting. So that means if t not t equal to 0, this function is 0. So that's how we define it. So that means if you pick any other value, it is not equal. So we use those two properties to define the Dirac delta function. So so let's write it like that. So what happened now? Let's say so Dirac delta function. Define a function. So define a function delta t with the properties there are two properties. The first property is so we can say that delta t equal to 0 if t not equal to 0. That's the first property. The second property is if you integrate this function, you get 1. So we're going to define a special function. These are what we call generalized functions. So we define the function using the properties. So we cannot actually say this is the function. So but we use these properties. So if there's a function like that with these properties, we call that is a Dirac delta function. That's a Dirac delta function. And then we talk about the generalized version of that. So what's the generalized version? So what we're going to do, we're going to talk about this case. We're going to shift this function a little. So we're going to define, we're going to shift the function to a point A. So so we can shift this function to A, and then what we can do, we're gonna go little smaller epsilon to the two sides. So this is A plus epsilon. Epsilon means a small number. This is A minus epsilon, the same idea. So it is only non-zero in this interval. So that's how we define write it. So this is what we normally call delta epsilon t minus a. So it's a shifted version of that. So this is not the Dirac delta function, but it's epsilon version of that. So and then again, so that this area is equals to 1. So that means we know that this gap is 2 epsilon. So that means this has to be 1 over 2 epsilon. So that when you take the area, so you can see that the area of this part is again 1 area, because it is 1 over 2 epsilon times 2 epsilon, so which is 1. Okay, so this is the generalized version of that. So so let's define the generalized version of the function. So I'm going to call the results. So we can write the results. So so let's start with the first one. So the first one is delta t minus a equal to 0 if t not equal to a. So that's the generalized version. So how we define generalized version. And also we have the integral version, and then you can see at um, t equal a, it goes to infinity. So it's a kind of, okay, so that's how it looks like. So at a it is infinity, because I mean otherwise how you can have area. So yeah, so you can see that it's not really a function that you can understand like that, but we only go with the properties. So we use the properties to define the function. And then you can see that this is a nice one to model the impulse. And then also, so what's other results that we have? See, the other one is if you integrate this function from negative infinity to infinity, that means the whole domain, you can see delta uh, t minus a dt equals 1. So that's the two major properties of this function. So that's how we define the function. Good. And then there are a few other things. What is the most important one for us is the Laplace transform. So let's talk about the Laplace transform of that. So the Laplace transform of the delta function. Okay, Laplace transform of the Dirac delta function. So I'm going to give the result. So we can use the again the definition. So we can say the Laplace transform of the delta t minus a is equals to, by the definition is you can say 0 to infinity 0 to infinity e to the minus st delta t minus a dt, and you can show that it is e to the minus as. So that's the result that we have. Um, so let's put that in a box because this is very important. So Laplace transform of the Dirac delta function t minus a is e to the minus as, and then you can see the proof of this one in the description. Uh, so we're going to skip the proof for the moment, but you can find that in the description. There's a link for that. Okay, so that's that. So it is the Dirac delta, the Laplace transform generalized function delta t minus a is e to the minus as. And then what's going to happen? So if so, let's write it here. If a equals 0, so if a equals 0 means the delta t function. Uh, then you're gonna get Laplace transform of delta t. So let's just plug in 0 here. So it is e to the 0. That means which is 1. So that's also you can remember as a result because sometimes useful. So the direct Laplace transform of delta t is 1. So you get 1. So you can see that this is not what we expect. Remember, we know that if the function is piecewise continuous and of exponential order, we know that there's a Laplace transform. The Laplace transform is simply 0 when, so we have this, so I'm going to say not for piecewise continuous, and exponential order functions, we know that the limit s goes to infinity, the Laplace transform is 0. So we expect that result, but that's not the case anymore. So for this special function, it is 1. That's never equal to 0. So that's the reason these are what we call generalized functions, because it does not behave as a regular function. And then also let's recall some other results just to make sure that we remember all of them. So so let's write them. So what are the results that we have? So we also know that the Heaviside function. So Heaviside function for the Heaviside function, the Laplace transform is u t minus a is simply e to the minus a s over s. And then also we had the shifting theorem. So we had the second shifting theorem. So second shifting theorem of the property. What it says that if we have u t minus a and then f t minus a, which is equals to e to the minus a, so you can see that term is there and multiplied by fs. So this is very useful when you want to find the inverse Laplace transform. So we have this result, and also so we have these two. We have that one for the Heaviside function, second shifting property, and also so what this says that, so in a kind of way, so you can see when you look at the Heaviside function, so we can write like a in a sense we write like that. In a sense, we can say that the derivative of the Heaviside function, is the Dirac Delta function. It's a kind of idea. That's why it's a kind of. So let's look at the graph. So if you look at the graph, you can see at A, you can stay there, and then so this is the u t minus a is suddenly jump to that value when it stays there. So and then you can see that there's a big jump at that point and then it stays there. So this kind of explain the situation. So we can think of like that. Just an idea. And also we have one more result. That's also you can find in the definition, but we are not going to use that for this clause. So what is that? If you integrate from negative infinity to infinity, delta t minus a ft. So what's going to happen dt? What's going to happen? It's going to pick up the value at a. It's a very interesting result. So when you have a, when you integrate this one, what's going to happen is it's going to pick up the function value at a. Again, you can find the proof of this result in the description, but we don't use this one for this class. And then also if a equals 0, what's going to happen is negative infinity to infinity, delta t minus a ft. So actually it's 0, so let's put 0 in there. So what's going to happen is if you put 0, so delta t ft, so dt, what's going to happen is going to pick up the value at 0. Yeah, so these are also interesting results. Some of them we have already seen, so you can find the proof of this one also in the description. So now what we're trying to do is we're going to use these results to solve certain problems. So before we solve problem, let's try to find some inverse Laplace transform. That's the first thing. So let's do that. Inverse Laplace transform. So example, find the. So let's do two problems. Find the inverse Laplace transform. So let's do the first one. Let's say L inverse s plus 1 over s. So you can see that this is strange. We have never seen anything like this before. The reason is we remember we know that all those function has to be proper fractions before. What's a proper fraction means? Proper fraction means the degree of the numerator has to be less than the degree of the denominator. But now with this we can talk about even things like that. So if you get a problem like that, what we normally do is we do the long division and we simply divide them. So once you divide, what will happen, you can rewrite as when you divide s by s, you get 1 plus 1 over s. You can write it like that. And then what we can do, we can split this. So once you split, it's a 1 plus L inverse 1 over s. But now we know that uh, the Laplace transform of the delta function is 1. So that means if you inverse it, so you simply gonna get delta t. So that means simply become delta t plus 1 noise means 1. So that's the answer. So the reason is we know that the Laplace transform of delta t uh, is 1. So we use that result. So we can have results like that now. So this can be useful later. Um, and then let's do another one. So how about this one? Let's say L inverse e to the minus 2s plus s over s plus 1. So you can have anything you like, but let's do something like this. Uh, so again, we can do a similar trick. We can split this like this. So we can write this one as L inverse e to the minus 2s over s plus 1, and then plus L inverse s over s plus 1. Now, how to handle s of s plus 1? So what you're trying to do, you try to create the term in the denominator in the numerator. So, so I'm going to rewrite this one. We already know how to do this. We did this before. And then, so what we're going to do here is we can write this one as s plus 1 minus 1. Because once you do that, you can see it is, if you divide this with that, you get 1 minus the other term. So that means we can write these 3 like that. This is L inverse. You can say e to the minus 2s, e to the minus 2s over s plus 1, and then plus, you can split this so as, if you divide s plus 1 with s plus 1, you get 1 plus, actually it's a minus because I'm going to pull the minus sign out. So if you pull the minus sign out, so it is L inverse, you have 1 over s plus 1. Now we know how to find inverse of all of them. So the first one is, remember when you have e to the minus as, so what we normally do is we first write the function, and then we're going to multiply by the heaviside function. In the heaviside function, in this case, you have to subtract 2. So that means you know that this function corresponds to e to the negative t. Thus corresponds to e to the negative t. So what you want to do is, it is simply you're going to replace the t by t minus 2. So that means for the first one you're going to get u t minus 2, and then e minus t minus 2, because you can see that you write e to the t and then replace each t by t minus this value. Good. That's the first function. For the second function, it is delta t. For the third function, it is 1 over s, 1 over s plus 1, that's the each function, so it is minus, in this case a, so it is a t. So that's what you get. So that's the inverse Laplace transform of these two functions. So now what we're going to do is we can do maybe 2 examples to see how to use this in a practical situation. So let's do that now. So let's talk about the impulse response. So impulse response. So again, that's the same situation that we were talking about. So let's say you have a situation where you're going to put a large force in a very short amount of time. So that's the situation. So these kind of problems you can write as a differential equation. This you can write it like that. That's a differential equation. L is operator, differential operator, and operate on x. And then you're going to give a very short like impulse. That's the impulse, like a large force in a short amount of time. So this impulse. So as we discussed earlier, the other situation would be like you have a spring and a mass system on some surface with some kind of friction. So there's a friction here. So now what we're gonna do, we're gonna put a large force again, like impulse like that, in a like t equals 0. When we say like that, that means you're going to put a force in the t equals 0 amount of time at that moment. So now what's going to happen if you just put a force like that, it's going to fluctuate. So you can probably write this differential equation like this. So we can, I'm just like writing numbers, okay? So it's x double prime minus 2x prime plus 3x equal delta t. So that's a kind of way we can write these kind of systems. Uh, and then you can see that here the L operator is the differential operator. So that means the second derivative, so it's a d squared over dt squared, and then minus 2d over dx, and then we have plus 3. So that is the L operator. We just pull the derivative part out. Actually it should be t, not x. So t. So that's the operator we are talking about, L operator. So that's the situation what we're trying to do, how to solve this kind of system. So now we can see we can actually do this, and then you can see that after you solve, what we are expecting is if you put a delta t, what is going to happen to this function, the xt, this is xt, how it's going to behave. And you can see that, so it's going to go kind of in a situation like that, depending on other terms. So let's solve this and see what you get. So as the first example, let's do this one. So example number 1, solve, or in other words you can say find the impulse response. Find the impulse response. Impulse response, okay, of this one. Let's say x double prime plus omega naught squared x equal delta t. Delta t means you can apply the large force at t equals 0. Let's say, just to make things easy, x0 equals 0 and x prime 0 equal 0. If not, you just get few extra terms. Now as before, we take the Laplace transform. So take the Laplace transform. Once you take the Laplace transform, what will happen? This can be x squared sx plus omega naught squared sx, and then delta t. Now we know that the Laplace transform delta t is 1, so you just get 1. Now what we're gonna do is, that's interesting, with just 1. We can isolate this term, so x squared plus omega naught squared, which is xs, equal 1. Now what we can do is we can divide. So we can divide this. So that means xs is simply going to be 1 over s squared plus omega naught squared. And you can see that this is very easy to solve. What we normally do is we're going to divide and multiply by omega naught. So it is s squared plus omega naught squared omega naught, and then you can see that it's very easy to find the inverse. Inverse is simply sine. So now let's take the inverse Laplace transform. Once you take the inverse Laplace transform, and you get the solution. So it's very simple. Now, so take the inverse Laplace transform. So once you take the inverse Laplace transform, you're going to see xt is simply L inverse xs, which is L inverse 1 over omega naught times omega naught over s squared plus omega naught squared. And you can see that this is simply sine omega naught t over omega naught. So what happened? It's simply a sine function. So that's why it says start as a sine function. So that means if you draw the graph of this one, so it should look like a sine function. So you can start as 0 with just a sine, and then 1 omega naught is just a scaling factor. So what's gonna happen? It's gonna go in a sine graph. So you just draw a sine graph. So that's what happened in this situation. So this height is simply, when you plug in that's the largest value, so that means it's going to be 1 over omega naught. So what happened? So what this says that, so in this situation, so if it is a spring mass system, so let's say you have the spring mass system without friction, because there is no derivative term, that means no friction. So what's going to happen? So no friction. If there's a friction, uh, x prime terms comes, but there's no x prime term. So what this says that, so if you apply a force in either direction, it doesn't matter depending on what way you want to measure, what we want to consider as positive. So let's say you apply a sudden force in this direction. So what this says that it's just gonna go, so that's xt, it's just gonna go like a sine function. That's what this says forever. So that's the xt graph. So if there's no friction, that's exactly what happens. So this is the impulse response for this problem. So if you apply a force like that, sudden force, and then if there's no friction, it's going to go forever as a sine graph. So we're going to see that there. So let's do one more example. Uh, so the next example. So let's do this one with some numbers. So example number 2. So let's say solve the initial value problem. 2y double prime plus y prime plus 2y equal delta t minus 5. What does t minus 5 means? Along with y0 equals 0, y prime 0 equals 0. What is delta t minus 5? What is delta t minus 5 means? That means you're going to apply the sudden force or the impulse, that's the ft function, at 5. So that's a 5. At 5, you're going to apply the sudden force. So that's what it means. You're going to apply sudden force, which is equal to 1 exactly. You're going to apply sudden force at 5. It's not 5. It's not exactly 1, but you're going to apply sudden force at 5. So you're going to start the system, wait until 5, you apply the impulse, and then you wait. That's it. So let's see how what kind of answer you're going to get for that. So again, taking Laplace transform, so we have 2 s squared ys plus s ys plus 2 ys equal e minus 5s. That's the Laplace transform of the Dirac delta function, because e minus a is a equal 5 in this case. So in this case, a equal 5. Good. Now, as before, what we want to do is just solve for yx. That's it. So to do that, and then you can see that so we have 2s squared plus s plus 2 times ys equal e to the minus 5s. So the ys is e to the minus 5s divided by 2s squared plus s plus 2. So we solve the problem in the Laplace domain, but you need to solve this for the time domain. So what we normally do is we try to find factors if we can, but in this case you can see that it's difficult to find factors. So what we normally do is we do the completing square. So let's do that. So what I do is I'm going to pull the 2 out. So once I pull the 2 out, you're going to get s squared plus half s plus 1. That's what you have. Now we do the we're going to follow the completing square steps. So what's going to happen is, so this e to the minus 5s over 2, we leave it, and then let's do the rest here. So it is s plus, take the half of the s terms, that means 1/4, we just did the coefficient squared, and then we try to adjust. So what will happen, when you square this, you get 1 over 16, but we need 1. That means you can add the missing term here. That means the 15 over 16. That's the missing part. Now we just need just a slight adjustments. So I'm going to leave e to the minus 5s over 2. So we have everything we need, but we're going to make the adjustment. So in this case, the a term is, you can see, square root 15 over 4. So we're going to multiply by and divide. So divide means 1 over. Write it like that. And then this is going to be s plus 1/4 squared plus we have square root 15 squared. So we can just write it like that. So that means this has to be square root 15 over 4. So we have everything we need. Now we need to write the inverse of this one. So how to write the inverse of this one? So you can see there's an e term. E term means you get the switching function, and then we have s plus 4. Let's highlight few things. So we're gonna see this plus 4. That means you need to have the shifting theorem with 1 over 4. So that means there should be e to the minus 1/4 t term there. E to the t minus 1/4. And also we have this term. So what this says, that this says you have the Heaviside function part. So those are the only two things you want to worry about. And then the general function has to be sine function, because it says it's a sine version. So let's try to write them now. So let's write so let's write that. So after simplifying, we have ys equals you're gonna get 2 over square root 15, and then e to the minus 5s, and then we have s plus 1/4 squared plus 15 over 16, and then here we have square root 15 over 4. So now what we want to do, we want to figure out what is this function is. To do that, you can see that this is a squared plus omega square situation. So that means in this case this is a sine function. So we understand this is sine omega t situation. In this case, omega is simply square root 15 over 4. So we have all the details that we need. So we can write now. So we can say since the inverse Laplace transform of 15 square root over 4 divided by s plus 1/4 squared plus 15 over 16 is equals to, so you can see so there's a shifting part, coming from here. So we can write that first. So it is e to the minus 1/4 t, there's a shifting term, and then we know that this is a sine function. This is a sine, omega is square root 15 over 4 t. So we figure out what the function is. So that's a function. So now what we want to do is we want to take care of the exponential part, so that we can do now. So what we want to do is we're gonna do that part now. So that what we normally do is at the end. So let's do that now. So what's gonna happen? So yt, which is simply the inverse Laplace transform of the ys function. So what we're gonna do is only thing that we have to do is we have to shift t by t minus 5. So let's do that now. So we have 2 over square root 15, and then you have the u function u t minus 5. What we want to do is you want to replace all the t in the function by t minus 5. So it is 1/4 t minus 5, and then sine square root 15 16 over 4t minus 5. So and that's the solution. And you can see a few things. So we notice that this is sine function, and then we also notice that there's a what we call the decay term. So see, there's a negative sign, that means it's gonna decay. So this is a decay term, the decay term, and then also we have a switch here. So that's a switching function. So switch. So what happened? That means until t equal 5, nothing happens, just stays there. But all of a sudden, you can see that the system start moving. So that means if you kind of draw this, so what happened here is, so we have the system, we have the spring and the mass system on a surface. So what's gonna happen? So let's say you're gonna measure xt this way. That's my xt, the position. So what we're gonna do is um, after 5 seconds starting the system, so you're gonna give a impulse, and after you give the impulse, so what will happen, what this says that it's gonna start moving like this. So it's gonna start there, so we wait 5 seconds, and all of a sudden it's gonna go in this direction because the impulse is on that, and then gonna slow down, and then at the end it's gonna stop. So and we can see that that's exactly what we normally see in a real situation. So if you have a system like that, if you give an impulse, that's going to go move far away and then going to slow down and stop. So so let's look at the graph. So we can graph this and see how it actually behave. So this is the graph of the function. So you can see that so this is the yt function, um, and that's exactly what we expected. You can see start moving at this time. So it's wait 5 seconds and all of a sudden start moving in that direction. So that is the solution of the problem. So this is the end of the Dirac delta function and its applications.